thanks so much for the invitation and the opportunity to speak here. Yes, there will be 3 lectures. The topic of the first lecture is going to be mostly reviewing the background mathematical material that we're going to be needing. So it's going to be about what is a general quantum system, or a more formal way of saying it is that it's some sort of introduction to von Neumann algebras for physicists, aimed at physicists or information physicists or information theorists. So just to see where we are going, I'll give you a summary of a bunch of points that I'll be making. Of course, the theory of von Neumann algebras is pretty large, and we're going to be going over a few set of statements that we're going to be needing that are going to be useful for us for the study of quantum field theory. Oh, by the way, maybe I should say this. So lecture 2 is going to be an introduction to modular theory, the so-called Tomita-Takesaki modular theory, which is basically a set of algebraic tools and techniques to study a general quantum system.
Just one request. Make it a little bit bigger.
Sure. Sure. Lecture 3 is going to be applications of modular theory to quantum field theory. So that's where we're going to go. We're moving towards quantum field theory. All right. So let me first make the set of, give you a summary of the set of statements that we're going to be needing from von Neumann algebras. We're going to go over them slowly, but basically I'm going to motivate why it's good or physically relevant to define a general quantum system as a von Neumann algebra. Then we're going to say that we know that infinite dimensional quantum systems often have different superselection sectors, inequivalent superselection sectors, whether it has to do superselection. And the parallel statement for von Neumann algebras is that infinite dimensional von Neumann algebras that are not type 1 are going to have inequivalent representations. So this is the mathematical statement that is analogous to this. And because we're going to be dealing with quantum field theory, which is a particular infinite dimensional quantum system that is not type 1, where the superselection sectors or vacua of the theory are going to be important for us. So that's why we're going to go over this point. Then I will like to highlight 2 important tools that we have to cook up or build general quantum systems. One of them is very trivial, it's tensor product. And the other one is the thing that is less known, maybe. It's called cross product. It's the thing that you have, we're going to discuss this a lot. You have a von Neumann algebra, which is a quantum system. You have a symmetry group that acts on it. And you enlarge your von Neumann algebra by the action of the group. So we're going to go over this a lot. This is going to be very, very useful. Just to tell you one, if you are interested in building examples, one statement that is at first going to look a little bit funny is that all the examples of quantum systems we have ever encountered could be understood as an abelian von Neumann algebra cross product with some group. This including quantum field theories and all that. So this is a very, very useful trick that I would like to highlight. And we're going to use it at some point. Or maybe I should use the board better. Then an important point in this lecture is going to be the fact that quantum field theory is a special infinite dimensional quantum system that is, in the language of von Neumann theory, von Neumann algebras, is type 3. But what I want you guys to think about this is that type 3 means that the unitary group, the set of unitaries in quantum field theories, is very large, is exceptionally large. So this is the intuition behind this type 3. You have a lot of unitaries, more than you would expect. And then I'll just comment on this cross product, and it's relevant for super selection sectors. So every time you have super selection sectors, super selection sectors are often related to symmetry groups, not always, but often are related to symmetries. And in the presence of symmetries, one of the things that happens is that if in a quantum field theory, if you have a region A and region B that are non-overlapping, the algebra of region 1 AB is not going to be the algebra of A tensor the algebra of B. So if this is true, that the algebra of operators in A and B are just generating, this is generated by these two guys, we say the algebra is additive, but it's generically the case that in the presence of symmetry groups, this property fails. So these are all the things that I want to go over for lecture 1. Some of them might be very familiar, but we're going to set the terminology and language to be using later once we deal with quantum field theory or use modular theory. Are there questions about the outline?
The symmetry group name is global symmetry.
Global symmetry. Although the story of gauge groups is not very different, but it's easier to talk about global groups. It's pretty much analogous, except that you have to. So in this language, unfortunately, there's really poor terminology. There's some sort of mismatch of terminology between mathematicians and physicists. What a mathematician calls a gauge group is not what a physicist calls a gauge group. So the terminology goes this way. What a mathematician calls a local gauge group is what a physicist calls a global symmetry. And what a mathematician calls a topological gauge group is what a physicist calls a gauge group. But I will not be talking about any of that. So for these purposes, we're going to be talking about global symmetries. I mean, the setups I'm going to talk about are super simple. All right. This is not the only unfortunate terminology mismatch. There are quite a few of them. OK, so as physicists, we often talk about, so here I'm talking about algebras. But as physicists, we often talk about the representation of the algebra in the Hilbert space. And every time I talk about Hilbert space, I talk about what I have in mind as a separable Hilbert space. So it's infinite. It might be infinite dimensional, however, still separable. So a quantum system, as we
Could you remind us what is the separable?
means that countable. So the separable Hilbert space, the dimensionality is countable infinity.
Okay.
It's a Hilbert space of harmonic oscillator.
Not any form, not a continuum in the spectrum.
Yes, no continuum in the spectrum.
But in general, in quantum field, we don't have that.
No. We'll come back. And I will particularly not talk about CFDs. I'll talk about quantum field theory. So, by that, I mean when you have boundary conditions at infinity so that your spectrum is discrete. But we'll come.
You have things moving past each other with various momenta which can be continuously tuned.
That's fine. That's not inconsistent with what I'm saying. But let's come back. I think when you say spectrum, you have to tell me spectrum of which operator, right? So in the story that I'm talking about, anyway, we'll come back to this. All right, so this C-star algebras, oh, sorry. Yeah, okay, so the algebra we're talking about is a C-star algebra. Let's start simple with this. That is represented on a separable Hilbert space H. So what is a C-star algebra? It's an algebra that has a star operation. Physicists call it dagger. It has a norm that's finite, so every operator is bounded. And on top of it, it has the C-star identity. It satisfies the C-star identity. The norm of A and the norm of A dagger are the same. All right, so in the language of Hilbert space, these are very familiar things.
Norm means largest eigenvalue?
I'm going to say in a second. So dagger is, so for an example, if you take the algebra of D by D complex matrices, of course, these guys generated. The dagger operation trivially does this, and the norm of an operator is defined to be this, which means that if you take a vector in the Hilbert space, if you take a sphere of normalized vectors in the Hilbert space, and after the action of some operator A, it turns into something like this, what is the largest eigenvalue? Right? The largest vector that it deforms to.
So it is the same as largest eigenvalue?
Yeah. If there are eigenvalues.
If, yeah, it's a nice enough operator. Fine.
Yeah. If it has eigenvalues.
You mean norm square or norm? Which one do you mean?
I'm in square because in this, in the Hilbert space norm, this is A dagger A. That's what I put it. This. Right?
This is square, it's still the norm square.
Oh, I'm sorry. Yeah. So yeah. Sorry, my bad. Yes, correct. You're absolutely right. That was silly.
So we're not talking about QFTs here at all.
Well, bear with me. For now, I'm defining quantum system and I'm giving examples. We'll come back to that. But the short answer to your question is that we could be talking about TQFTs, but in these 3 lectures, I will not touch upon them. You have to massage some of these assumptions. All right, so what is a state? Oh, by the way, one thing to know is that von Neumann algebras are all C-star algebras. So they're special C-star algebras. In finite dimensions, there's no distinction between the two. We'll come back to this. Sorry? I have no idea. Sorry. Maybe. Okay, so
I'm sorry. So this is the algebra is the algebra of operators.
correct.
Operators acting on a Hilbert space.
No, so the algebra, this is defined algebraically, abstractly.
Okay. So
The Hilbert space is a representation.
okay. So this dagger operation is just some abstract.
Some
algebra.
abstract. The norm and the dagger are both abstract. Now, in this, I gave you an example,
Okay.
right? In a particular representation, I give an example. These are very abstract objects, right? And we would like to talk about abstractly for a reason that is going to become clear in a second. So what is a state? I said this is a quantum system, abstractly. So what is a state?
Sorry, dagger is not defined as an action on some vector space and being able to.
At this level, it's just defined abstractly.
There are two. There's an algebra with 2 operations, dagger
Yeah.
and star.
So some involution.
Yeah, it's just like some formal definition. So as I'll come back to this. So a state,
Dagger and
state is a map from the algebra to complex numbers, right? So that is linear and positive. So how is this familiar? Well, in this example, states are density matrices, which are linear positive operators with the property that you give me an operator, rho defines for you the expectation value. So this complex number is the expectation value. Sorry, I should put it this way. Is the expectation value to every operator there, and This is an algebra of observables. Oh, by the way, maybe I should have said that. Observables are all self-adjoint. In an algebra, we have an addition operation. We want to add them with complex coefficients. Therefore, we're going to have, in general, operators that are non-self-adjoint, and then expectation values are going to be complex. And of course, this is a linear operator. Linear is a linear map. This is a positive operator. What does that translate to? So positive operator here means that if you diagonalize this thing, it's self-adjoint as well. If you diagonalize this thing, all these guys, eigenvalues are non-negative. Here it means that omega of A dagger A is always non-negative. Good. So again, formally, this is what the definition is. And then, so this is a representation I chose. There is another representation that I can choose that I'm going to write down, which is going to be more useful than this representation.
Here it uses positivity of the norm of A.
Positivity of norm. There's no assumption. So A dagger A is always positive.
That's a definition of what it means.
Yeah. A dagger A is always positive.
Then there is another definition here.
No, that's an example.
This is an example.
If you take it, there will be a consistent, and the question is about the consistency of that with that. So there you are using the fact that the norm of A is positive, right?
I mean,
So here I just said that every linear positive operator could be.
it'll be K A, A dagger K.
Yeah.
So it'll be the norm of the state K A on K, and then summed over K. So it's sum of positive numbers.
Yeah.
Sorry, A is not rho.
What?
Omega is positive.
So
Omega is positive, but omega is rho. Sorry. So suppose rho is this.
Yeah.
Now put your operator.
so it's gonna become like this. Sum over.
For all A. For all A, omega A dagger A is greater than 0. So this positivity is a property of omega, right?
So you see, the positivity is that this has to be positive for all A squared, which tells you that PK should be non-negative.
Right, but then you are using positivity of this A squared, right? Which
Well, A squared is always positive. A dagger A is always positive.
Choose an operator that's A dagger A,
Yes.
and this should be positive.
Well, you didn't say that anywhere there. That's why I was asking.
Oh, I'm sorry. So here's the thing. That's right. So every self-adjoint operator in the theory of C-star algebras admits a self-adjoint admits a spectral decomposition, and then we call it positive if and only if all the eigenvalues. The whole spectrum is non-negative.
Yeah.
Sorry, I should have said this.
Actually, I didn't understand. I thought you defined what A dagger was. Now
Yes.
suppose I take an algebraic element A dagger A,
Yes.
and I'm going to define this map as positive as long as omega on A dagger, any object that's of the form A dagger A is positive.
Correct.
That's my definition.
That's my definition, but I just said that A dagger A is always positive, but I didn't tell you what I meant in the algebraic side by calling an operator positive.
Okay.
That's all.
But, right. But I'm saying that if you just take the definition of A, no, the omega of anything
Correct.
that is of the form A dagger A.
That's my definition, indeed. That's my
Well
definition.
stated, and it's clear in this example.
This is an example. That's right. Okay, good. So now there is another representation of the density matrix I can use, which is, in the language of physicists, is purification. Purification, which is, it's the same state is represented by a purification of rho in the following way. You introduce an identical second copy auxiliary system, and you purify rho. You have to take a square root of pk. Now, if you take this state and reduce it to the algebra of A, you're going to get rho. And the density matrix on A prime is also rho here in this case.
What is the statement?
So
Purification of what?
so this is density matrix.
Okay.
A density matrix always admits could be represented. The information content of density matrix could be represented using a pure state of a duplicated Hilbert space. And thermofieldable, exactly. But this is a canonical purification I wrote down. So purifications are always ambiguous up to a choice of a unitary and on A prime, right? So this is a canonical purification I wrote down. Why is it canonical? Because it's symmetric. This U prime is fixed by requiring the density matrix of A prime to be rho as well. But I'm not going to use that for now. Good.
And in that definition, it follows that rho is diagonalizable
Which definition?
from that definition.
There's no rho here. One of the reasons I'm doing this is that in general quantum system, there might not exist a density matrix. So
Right, no. So here you are giving an example, right?
yes,
Omega. Omega is a state, right? Which
Correct.
is a map, linear positive map
correct,
from A to C.
correct,
And rho is an example of such a map.
correct. In a particular algebra that
Yeah, in a
admits
particular algebra.
that admits density matrices.
Right, but even in that algebra, can I consider rows that are non-diagonalizable and still be a state in that sense?
No, no.
Why not?
Rows.
It's always
So
trace of row A, right?
when I said it's positive, it's already implied. So I want to define. Yeah, the positivity already tells you that this is
Sorry, the positivity you gave me this thing, this criteria already, right?
correct.
So why do I have to use your definition? Because I could just do trace of row A, that would be this map. That would be a map from A to C.
Yes.
And I just check whether that map on A diagram is always positive or
So
not.
you're saying that you're asking whether or not there exists maps in the algebra of d by d complex matrices
Yeah.
that
Are
is
not
linear and
diagonalizable.
positive, but doesn't have a representation as a diagonalizable
Yes.
density matrix. A diagonalizable operator, I believe there is none, but I haven't shown you here. I believe there's none. Yeah, I have not shown it here. Okay. Good. So now let's define something that's going to be important for us. We say this is a property of certain states. We say a state has the Schlitter property if and only if. So now first let me give you the intuition here. If it's a density matrix, all pKs for all k are non-negative. There are no zero eigenvalues. Let me first, I'm going to finish the definition here. So I have to say one more thing. So one of the uses of this algebraic language is that there are situations, there are quantum systems, such as quantum field theory, where there are no density matrices, right? In those cases, when there is no density matrix representation like this, the representation always comes in some purified language. If you construct representations of this guy in full generality, always comes up as some purified language. The analog of that, we say state is Schlitter. The analog of this is the statement that A acting on omega of A prime, closure of this is the full Hilbert space. So let's,
Roughly, if omega in a quantum field theory, if omega was the background state, then this will be the statement that background cyclic and separable.
so yes, but
Okay.
Sorry, I don't know what's
no. Yeah, let's not introduce new notation.
Just to get the intuition, this will be the statement, right? This statement means
No, this does not imply that. So I want to define something. So this definition doesn't imply anything yet. The definition is that I call a set of states Schlitter if and only if the algebra acting on this representation is the full Hilbert space. Now it is going to become related to cyclic and separating thing, but
using Schlitter theorem in a quantum field theory, if omega represents a vacuum state,
so Schlitter theorem says the vacuum of Poincare invariant quantum field theory is Schlitter. That's what it says.
Exactly.
But I have not used that said any of that.
you have defined it, but to get
Yeah.
the intuition.
I'm just talking in terms of a general quantum system at the
This
moment.
H here is just the H of A or the H of the tensor product of
I will say in a second. So the analogy to have in mind is something like this.
this what the subscripts are.
I will explain in a second. The analogy to have in mind is like
In the
this.
sense of dense. You don't want equality, you want it to be dense, right?
Allow me to bear with me for a second. If I have a quantum system, okay, so let me even make it simpler. Left and right wedge. So the picture to have in mind is like this. This is quantum field theory that I've split into Rindler wedges left and right. This is to be compared with a quantum system with A and A prime. There is an algebra of operators on A here. However, it does not admit a representation in terms of a density matrix. The algebra of operators here is D by D complex matrices. There's a representation in terms of operators in this Hilbert space. There is a Hilbert space of A. Here there exists no such a thing as Hilbert space of A. In quantum field theory, we only have the Hilbert space of the full thing. We only have the representations of this type.
This is UV divergence. You basically want to mean that you have UV divergences if you want to talk about.
Yeah, but formally, the quantum field theory, we're going to define in such a way that there's no UV sense in it. This is a particular set of algebras.
I didn't quite understand. I mean, there could be a Hilbert space of the left render guys themselves and the right render fellows.
In Poincare invariant quantum field theory, there cannot exist a Hilbert space of the left in quantum field theory. If you did construct such a thing, all the perturbative, your vacuum and all the perturbative excitations are going to have infinite energy. There's not a single finite energy state in that Hilbert space. But
So energy with respect to boost?
no, in respect to the Hamiltonian,
I mean the standard type.
P0. I think these are going to become clear with examples later on. But what I want to say is that I know that I'm not motivated. I'm just giving you analogies for now, but this is going to become hopefully clearer later. So in quantum field theory, we only talk about the Hilbert space of global states, right? This Hilbert space is always separable, infinite dimensional, however separable. And it's actually let me not jump ahead of myself. Okay, so now here, I said A of A acting on the vacuum, the closure of it is dense in the Hilbert space. What does it mean? It means that if I take the, I shouldn't have said vacuum, Riesch-Litter state. If I take a Riesch-Litter state here or here, by acting only on this side, I can generate arbitrary excitations on this side. How can I arrange for such a thing? This is the way to arrange for it. If I take a state like this, by acting with arbitrary operators here, I have access to excitations on A prime if my pk is non-zero because of entanglement.
Wait, what is the meaning of this kind of notation? K comma K?
As the same thing.
But you just said there is no Hilbert space for K. A.
I'm just discussing this case. I'm discussing this case for now, right? So if you have entanglement across, if your state is entangled, then you can excite this mode by acting on this. Now, when pk is positive for all k, it means that every mode is entangled. It means it's completely entangled. This is not the same thing as maximally entangled. This just requires pk's to be non-negative, or the density matrix to be invertible. The analog of that in a quantum field theory or general quantum system is that by acting alone on A, on your state, you can generate arbitrary excitations out here or here.
Sorry, like Abhijit, I haven't understood what that second picture means. The A and A prime. What is that? What is the Hilbert space of A and what is the Hilbert space of A prime?
So isomorphic copy. So H of A prime is an isomorphic copy of this.
But what is H of A?
H of A is so in the case of finite quantum systems, S,
But I thought we were talking about quantum field theory.
no, I'm doing an analogy here. So this is, again, this is to be copied here, right? Left is left, right is right. Right is the analogy of, is the case of D by D complex matrices, and left is a general quantum system. And I guess I ran out of board space, but what I wanted to write was that if the set of states for which pk's are positive for all k on this side show the same behavior as the states for which A acting in the vacuum is dense in the Hilbert space.
So let me try to summarize this. So you're saying suppose I have a finite dimensional Hilbert space.
Yes.
And I take two copies.
Yes.
And I have a state of this form.
Yes.
When one of the two Hilbert space, any state in one of the two Hilbert spaces is Riesch-Litter in the whole space.
Yeah.
Is that right?
Yeah. This is the definition for quantum field theory. For general quantum system. Now, in my example of finding a quantum system, this definition reduces to this simple fact when there are density matrices. But general quantum system, there aren't density matrices, so this is a definition. This is the definition that belongs on the left side.
So let's say omega is some state in the quantum system.
Yes.
Then A with subscript A means what?
The algebra of this.
But
So,
what does that mean?
oh, well, I'm going to give explicit examples. But there, in quantum field theory, there are no local density matrices. However, there are local algebras. But I can give you a quick answer. Take a fermionic theory with some in 2 dimensions, and this, for all bounded functions, x supported in A is one of such operators. This is a bounded operator for fermionic theory, and yeah.
So that H over there in that equation is HAA prime? Is that
Correct. In quantum field theory, there exists only this guy. So in systems with density matrices, there's a tensor product like this. In quantum field theory, this is not true. There is no H of A. There's only this. Sometimes people say there is no tensor product in quantum field theory. That's what it means. There's another way of defining it, but anyway.
Are you saying that the state you have written at the top of this board is that does not exist in a quantum field theory because I've separated in
Well,
space into A
correct.
and prime.
There exists no. This was in the context of this example. Yes, there exists no such
In
state.
quantum field theory, I can't have that state.
No, you just don't have the algebra doesn't have this structure. It's a property of the
All
algebra.
of the Hilbert space of the quantum field theory is being produced starting from that state by acting algebra.
No. It's not in quantum. The difference between quantum. I think I should have made this clearer. So the difference between quantum field theory and the particular systems of called type 1 that have density matrices is a difference in the algebra. There is no tensor product. So it doesn't even make sense to talk about states of this type with pk positive or not.
why not exactly?
Why not?
Yeah, why not? I mean, what's wrong with it? I didn't quite understand what's wrong with left regular.
So
and right regular.
at this point, let me just take a very mathematical point of view and say there exists algebras for which this is true. Now, I haven't argued for you why quantum field theory is one of such algebras.
I mean, any state at short enough distances looks like a vacuum, and the vacuum is entangled. Let's take a little interval that encapsulates that cross point.
Yes.
That at short distances in the vacuum has entanglement between the left and the right moving parts. And every finite energy state at short enough distances will have that property. So if you've got a state where, it's only on the left, only on the right, it will necessarily be infinite energy.
Or, yeah,
Entanglement assumes factorization.
this is the picture with a cutoff. So what Shiraz is saying is that if you thought of quantum field theory with a cutoff, this would be the picture. But I think by the end of this lecture or maybe another lecture or next lecture, it will become clear what I'm talking about. Because I have not given you many examples yet. I have not, when I talk about quantum field theory, I usually jump ahead.
So you're saying quantum field is inherently different from lattices with the cutoff and so on.
Yes, quantum field theory is not a lattice system. It's fundamentally different.
And not just having to do with gauge theory, it's just any theory.
This is any theory. Any quantum field theory is of different nature. Its algebra is of a different nature from a system on a lattice. Correct. And it has to do with the Poincare invariance. There exists no system on a lattice, no matter how small, of a cutoff that has exact Poincare invariance. If you require Poincare invariance in the strict sense of it, there won't be a factorization, period.
And when you say A with the subscript A, is there a follow-up condition on the support?
Sorry, where? This?
Yeah. Is there a particular meaning to that?
Oh, yeah, it has to be it has to be supported only on A. It can't have tails outside. It cannot have tails outside. So mathematician will tell you that it has to be Schwartz function on A. However, that's a little bit too strong for a physicist. We can talk about this offline. But any mathematical physicist would define it as a Schwartz function.
What is the Roman A, not the
Algebra.
The Vertigo is the A.
This is the algebra.
What's the other thing? Is it the space
Region, yes,
What's space-time?
correct.
But in the algebra, there's no notion of space-time yet.
So we'll get to all of this, but in quantum field theory, we want to associate to every causally complete region of space-time an algebra. Then there will be some sort of a hierarchy of them. If space-time region sits inside the larger one, this is subalgebra of the larger one, and so on and so forth. There will be causality encoded in it. Yes.
You already said it that although the state itself does not admit a local interpretation, there does exist a local algebra.
Yes, this is going to be key.
From your definition of state, it was not clear what local.
Yeah, okay, that's right.
A prime is just the state corresponding to an algebra for
Omega A prime, yeah. This is a vector. So to clarify, I'm going to use a mathematician notation convention, which I find it easier. A state is what I defined. This is a vector in the Hilbert space. A vector in the Hilbert space could be a representation of a state. This is a mathematician language, which I find very clear in this setup. So I called it pure state. I should have said vector. All right, so this is actually an important comment. So why did you, why don't we talk about, if algebras are so important in quantum mechanics, why do we do physics without talking about algebras? It's because of a theorem that von Neumann and Stones proved it, that for a class of systems that are to be defined later, I'll define it later, but in this lecture, called type 1, that includes all the systems with density matrices. So all the systems with density matrices. The following statement is true. Given an algebra and a state,
So by that I can assume, I can just say that all the systems with the tensor product, inverse space with the tensor product structure.
you could say that. You could say that. But this, let me give examples. Examples are any finite dimensional, actually this is an exhaustive set of examples. Any finite dimensional set system, algebra, and any finite number of harmonic oscillators. So any finite dimensional quantum system, or if it's infinite dimensional, it has to be isomorphic to a harmonic oscillator. Now, d copies of harmonic oscillator is isomorphic to it. All right, so there is a machinery, I will not discuss it here, called GNS construction. It's simple, but it's a prescription that mathematicians invented that given an algebra and a state, you construct a representation of that algebra in the Hilbert space. This is something that they've done. And the statement of Stone and von Neumann is that if the algebra is type 1, it admits a density matrix. If you change the state, the new representation is unitarily equivalent. So up to a choice of a unitary, you have one Hilbert space. The choice of the state is somewhat irrelevant. The choice of basis. However, this is no longer true for systems that are not type 1. Importantly for us, in quantum field theory, given an algebra and two different states, after you do this GNS quantization, construction, you end up with two different Hilbert spaces. So, sorry, you end up in here, you represent omega with a vector in the Hilbert space, omega prime with a different vector in the Hilbert space. As you act with this guy on the algebra, oh, sorry. These are not unitarily equivalent. These are not unitarily equivalent. And this should be familiar in quantum field theory. These are different vacua. These are different superselection sectors. For instance, if you take as your omega, if you can consider quantum field theory in the vacuum, or you can consider finite temperature quantum field theory. These two systems are not in the same Hilbert space, are not described in the same Hilbert space. Why is that? Because all the excitations in the vacuum are going to be finite energy. You will never be able to excite the system enough so that you come very, very arbitrarily close to the fine temperature state. All such states are infinite energy.
I'm sorry, just
No worries.
so given a type 1 algebra with a density matrix.
No, type 1 algebras do have density matrices. So all type 1 algebras have density matrices.
Okay. What does it mean that an algebra has a density matrix?
Sorry. A type 1 algebra that I'm going to define in a minute will have the property that all its states admit a density matrix representation.
So all its states in a representation of the algebra acting on a Hilbert space is represented by traits with a density matrix.
Correct. Correct. But I guess this is just like I was trying to connect it. This is not a very precise language. I will define this in a second. I was just using that analogy.
Sorry, and I just want to make sure I understand each of these. So what did you say here again? You've got an
So-
algebra and a state, and that gives, this GNS construction gives what? What is
A
it?
representation of the algebra for choice of omega. So
representation as operators acting on a
Hilbert space, indeed.
Okay,
So which means that it associates to omega a vector in the Hilbert space, and then so you found one vector. This you call this ground state or vacuum. Operators in the algebra acting on this vacuum will be excited states, and these generate. You prove the axiom that it has a Hilbert space structure.
But what was that? I'm sorry. Really
No
sorry.
worries, no.
So under what conditions is this true?
No, this is a prescription I haven't described to you. Mathematicians construct a prescription. I have not.
Every algebra and every
For
state?
every von Neumann algebra and a choice of a state, they construct a canonical representation called GNS.
Okay. Type 1. So what's
No. There's no type.
What's a von Neumann?
I define what a C-star algebra is. That's my next comment.
So just to be clear, a state, what we call the state here is different from state in the Hilbert space.
So
Called in a-
states are linear positive functional on the algebra.
Those are like density matrices. In this particular.
In this example, yes. In these examples, yes.
For type 1 especially,
Yeah,
the
yes.
state on the left-hand side is basically
Yeah, okay, sorry. I think I should go slower because, good. So let me first answer your question. So I define for you what a C-star algebra is, which is just an algebra with a star operation and a norm that satisfies what you would expect from a star. So if your algebra is infinite dimensional, I haven't even defined for you what it means to be infinite dimensional, but you have a sense of it. I will define it later. Then you will have to decide, as physicists, what do you mean by a limit of operators? So we say, so if you have a sequence of operators, an, inside the algebra, for such that for any two vectors in the Hilbert space, the limit of n of an, this is equal to psi a phi. So for all psi and phi vectors in the Hilbert space, we say that limit of n, weak limit, so weak operator limit of an is a. So this is just a definition.
And this
Yeah,
definition,
so this is sorry.
this definition requires the algebra to be implemented on a Hilbert space.
Yes, but I can always do that.
You can always do that, and it doesn't. It requires this is true for every possible implementation of the Hilbert space. Then maybe it equals-
No. So this is going to be important. If the algebra is infinite dimensional, it will depend on the implementation.
But this definition of this limit of operators,
Yes,
will that also depend on the implementation?
correct.
It will.
Correct. It will. It will. The
Okay.
limits will.
So then it's not a definition on the algebra, it's a definition on the representation of the algebra.
So at the moment I define, yes, this is a definition on the representation. Indeed, that's very good.
So this A, that limit thing, that should in principle have a label called omega as well.
Very, very correct. This is a Hilbert space statement. Correct. It's Hilbert space statement. Correct. This is a representation statement. So now we say an algebra is von Neumann algebra. A C-star algebra is von Neumann if every time the weak operator limit of an is a, you include a, you add a in it. So you include a in it. Or said differently, if a C-star algebra is closed in weak operator topology, it's a von Neumann algebra. So why is this physical? As physicists, the things that we measure, even though we call self-adjoint operators observables, the things that we measure are matrix elements. That's what we care about. Now, how is it possible for two operators to be not equal but have the weak operator topology? It is possible in infinite dimensional Hilbert space that the result of every single matrix element is arbitrarily close. However, because it's infinite dimensional, so if these are closed by 1 over square root n, there are n squared terms. So the operators might be widely different. However, matrix element by matrix elements, they're the same. As physicists, we only care about matrix elements because those are the things that we measure. Therefore, we want to close the algebra. We want to equate this. We want to close the algebra in weak operator topology. Notice that this distinction comes up only in infinite dimensions, right? So in finite dimensions, C-star algebra is what you need to know.
So these algebras have a norm, right?
Sorry?
These algebras have a norm.
Yes.
So we can also define a limit using the norm. The norm is goes to 0, the limit goes to 1.
The norm goes to which norm?
Norm of an minus a.
No. That's not the same. So that's not the same now. Norm.
It's not the same.
It's not the same.
Also not the preferred definition of the limit.
No, that's not a preferred thing either. That's the strong norm. So
Here, can you give an example? Sorry,
yes.
maybe you can finish there. But here, can you give an example of how you choose a density matrix and associate a vacuum to that?
Oh yeah. So then this is exactly the language I use. So density matrix, diagonalize it, and take, for example, the vector that was the canonical purification of the density matrix. This was that omega that I wrote square root of pk sum over kk. One instance is that. That's exactly what pops out of GNS construction. So GNS construction always gets you these canonical purifications that are symmetric, and they're like thermophile doubles.
That is a state in some double Hilbert space, right?
Correct.
But you want a vacuum in that Hilbert space, the one that you were talking about, or you want to just some vacuum in some Hilbert space?
Yeah, some Hilbert space representation. Right. All right. So this is now let me make one statement that is might give you a little bit of a headache. It comes back to your question. This is the part that physicists might a little bit get annoyed, but I think if you spend a little bit of time thinking about it, it's reasonable. So every time we talk about, we are only after representations of algebra on separable Hilbert space. So what is an example of a separable infinite dimensional Hilbert space? The algebra of bounded operators on a separable Hilbert, sorry, what's the example of von Neumann algebra on a separable Hilbert space? Is the algebra of bounded operators on the Hilbert space, right? Bounded operators in the harmonic oscillator. All the operators of type this and the harmonic oscillator that are bounded. And we defined what bounded means. This algebra is called B of H. It's very important. Otherwise, it's type 1, and it's called type 1 infinity. Infinity just means infinite dimensional. So every time, when we say we're after representations of our algebra in separable Hilbert space, it means that our algebra of interest is going to be subalgebra of this 1 infinity. So all the algebras we'll ever talk about sits inside this guy. This representation, okay, maybe I should not jump ahead of myself.
I'm sorry, I got something wrong. So if you have a single harmonic oscillator
Correct.
in Hilbert space, and if I take the Hamiltonian of that,
Yes.
That's not bounded.
That's not bounded, it's not in the Hilbert space. However,
Not in the algebra.
it's not in the algebra, sorry. However, these guys are.
B of H thing is only the bounded operator, something.
Correct. That includes time evolution operator for arbitrary time, However, not the Hamiltonian. Sorry. Yeah, that's correct. Good.
Now will you say why quantum field theoretic inverse space is separable?
Is what, sorry?
Is separable, quantum field theory inverse space is separable?
Oh, it's the statement that
Will we postpone it?
yeah. No, we'll postpone, but let me give you a quick example. So put quantum field theory on a circle, right? We're going to be talking, the algebra is over here, but that algebra is always a subalgebra of the algebra of the theory on a circle, which is type 1 infinity. So quantum field theory on a circle, the full theory is always type 1 infinity isomorphic to this algebra, right? Now, the algebra of this region is a subalgebra of that, therefore it sits inside harmonic oscillator, always.
So there's some assumption about compactness or something?
So it's not quite the compactness, but we want some sort of a gap. We want some sort of a gap. That's why CFTs are a little bit harder to define.
CFTs on spheres are perfectly nice, right?
There's no problem with CFTs on sphere. In this language, we're only talking about CFTs on sphere. We can make the sphere to be arbitrarily large. Who cares, because it's CFT. But quantum field theory in flat space, when we discuss them, we assume a gap. There are ways to deal with it without a gap, but let me not get into those complications. All right.
This seems like an important thing, right? Because gap in gapless is an important distinction.
Correct. But here, you would say a CFT is a gapless system.
No, but not just the CFT. Even the thing with the gap, the continuum can start after a gap also. Two-particle continuum.
Yes. Yes.
So
Indeed, generically, that's the case.
theory with some
Yeah.
two-particle continuum.
Correct.
So if you assume some compactness, perhaps there could be some spacing having to one-on-one. But otherwise.
Yeah. Here, all I need is just a gap.
Okay. So
All I need is a
states
gap.
afterwards.
Correct.
After
Yes.
vacuum.
There could be two particles.
That's why you
Yeah.
insisted on not considering CFTs.
I think, yeah, CFTs are a little bit icky. CFTs in infinite space are icky.
And what was the final statement that is that B of H? Well,
It's a particular algebra that's important for us.
Okay.
It's the algebra of bounded operators of harmonic oscillator. It has a name, 1 infinity. Well, I'll refer to this algebra.
operators of a single harmonic.
They're all isomorphic. If you take k of them, it's the same algebra. But this algebra is very, very important because it's the largest algebra we'll ever talk about. And I keep referring to this algebra all over and over again. This algebra has density matrices. Okay, very good. How is the time actually? Okay, because I'm pretty much.
So the standard known operators like x and p and stuff like that,
Yes.
they are all bad. So you have to work only with e to the power I x, e to the power I p.
Oh yeah,
that
yeah,
kind of
exactly,
stuff.
exactly.
So Hermitian, okay, of course you can still have.
Or no, here.
Hermitian.
Here's an operator that's bounded and self-adjoint is all nice.
And Hermitian.
Yeah. Well, actually, sorry.
Yeah.
Yeah, sorry. That was important. All right. So now I want to go through a bunch of examples, and I'm going to pick somewhat weird examples, at least at the first look. So examples. So I started by saying that a one-Neumann algebra is a general quantum system. So can we recover classical physics from this? This example of classical physics is actually particularly instructive. So take an abelian von Neumann algebra. This is a general quantum system, a classical system, right? So what is this? A mathematician will tell you that an abelian von Neumann algebra is unitarily equivalent to the following thing: the algebra of bounded functions on some measurable set x mu. So what you have is some set x with a bunch of points in it, x1 to xn. It's measurable. What is this algebra? So you look at bounded functions of this. The addition is defined just point by point addition. multiplication is defined point by point multiplication. These are complex functions. Therefore, f dagger of x is fx star, so complex conjugation. And then the norm of f is the supremum of x in x of x. Okay, so this is the most general classical system. Classical system.
The number of x's had to be finite in your
No. I just, yeah.
It can be infinite, but it has to be countable.
It has to be a measurable, it has to be a standard measurable set. A system, that's like, that's a basis of probability theory. So, yeah. Now, what is a state?
Could be an interval, could be a
Yeah. In a measurable set. What is a state? State is a linear map from this algebra of functions to complex numbers, right? For instance, a state is basically a probability measure. How omega of f is going to be something like this, which is d of x, p of x, f of x. So now, for this reason, it makes sense to identify omega with square root of p.
Where p of x is pointwise positive.
Correct. It's a probability measure. Yeah, p of x, yeah, exactly. Now, this is one state. Where are the other states? The other states are, as I described, you take one of these vectors, you act with some function on it, you normalize it, and you get an excited state. In this excited state, the expectation values are defined in the following way. Oh, by the way, I forgot to say, what is the Hilbert space? Hilbert space is a set of square integrable functions on x, right?
This X is a phase space rather than coordinate
Correct.
space, right?
Well, okay. It's very similar to phase space. There are subtleties. Yeah, there are subtleties. Because in my next example, you'll see what the difference is with phase space. But before actually talking about that, a lot of these, what I'm going to talk about.
Gautam, could you explain that? How did you see it with phase space?
I mean, in the sense that when I define a state, I can say that the state I define by saying that P is P naught and Q is Q naught. Okay, so that's a delta function kind of distribution. So he is saying that, okay, I'm not going to use delta functions. I'm going to use a
Probability measure, yeah.
in the P and Q thing. And the delta functions, our normal initial conditions, which define the state in the system, they are like the delta function limit, and instead of that, he's using some kind of weight bracket kind of stuff.
Yeah.
But
You can use linear distributions for a given state.
But you have to.
There's one difference.
This expectation value that he has done here, that has to be clearly dp kind of expectation.
So yeah, you could if you take your x to be set of positions and momenta, and then your states become probability distributions on that, then it's
Why
the
square
standard.
integrable? Where did that square integrability come from?
To get a Hilbert space, you want vectors that are norm 1, which means they're square integrable. Because we're insisting on this is a classical system. I didn't need to insist on Hilbert space. However, because I want to put it in the same framework as quantum mechanics, I insist on square integrability. All right. So I wanted a lot of what I say in these 3 lectures are related to information theory.
I normally think of square integrability because the square let's say the square gives you a probability.
Correct.
And then the integral of that probability should be equal to 1 and therefore in particular.
Yes.
In Gautam's thing, I thought that P was itself like the probability. So P squared is slightly odd.
Yeah, I mean, I
No.
also don't understand.
Sorry, there are 2 things. The P is P. So there is P of x, which is never squared, but G of x is squared. G of x is my excited state. This is the thing that's square integrable. P of x is never squared. P of x is just like, yeah. So if you look at this, there's no squaring happening.
Yes.
That's why I identified omega with the square root of P.
This notion that you can describe a space by looking at functions on space. Typically,
Yeah.
in classical mechanics, we look at the phase space itself. But there is this equivalent viewpoint where you just look at functions on the phase space. And for to have nice functions, I guess you need that to be squared.
No, but I thought we were talking, the functions were essentially a probability distribution on phase space, I thought.
Yeah, like
So,
in a way,
I think-
Wigner, if you take the Wigner distribution for a particular wave function, then what you would insist on is just the integral, not the square of the Wigner.
This is different from phase space for reasons that are going to become clear. It's superficially related, but for the reasons that's going to become clear.
Okay, fine.
Because I'm going to do quantization of this using cross product. But we'll see, it's different. But before that, let me sorry.
Mod G,
Go ahead.
Mod Gx squared would have been the probability distribution if this were a quantum system.
Mod G squared?
Yeah,
So you have a state G.
Yes.
So mod Gx squared is like the square of the wave function.
Yes.
So this is natural.
Right.
That would be thought of as a probability
Yes.
distribution of
Yeah.
states.
You can think of it that way. Yes. So a lot of what I say in these 3 lectures are about information theory. So I want to draw a connection with information theory at this level to classical information theory. And here's how it goes. So you have think of x as a random variable. This is the set we're talking about. Or if you wish, this is the alphabet in your information theory. X's in X are your letters. Your messages look something like this, a bunch of X's. Your state is a source that produces letters with some probability distribution P of X. So the task of information theory, maybe this is a little bit formal, but in information theory, this is how we go about defining things. You have a random variable. You have a source that produces letters with probability distribution P of X. Then you talk about, this is your source. This is producing some message. In the limit of these messages being very, very long, how well can you compress them? An important piece of intuition that's related to entropy and all that is about how to compress messages and express them in terms of a smaller, more efficient alphabet, smaller alphabets. And entropy of a probability distribution tells you how much you can compress so that you could recover. So you can compress and decompress with small errors, controlled errors. So let me draw an analogy. You have a state. What you want to do is that you want to compress the state. So state is represented in some Hilbert space. You want to compress the state, meaning that you could come up with some sort of approximate representation in the smaller dimensional Hilbert space. So that you might have lost some certain things, but you would like to be able to recover that information and in a certain limit. It's controlled. So this is one analogy. Maybe I should make the second comment as well. No, let me come back to this.
So now you're using a different language from Hilbert spaces and algebras and stuff like that.
I'm drawing an analogy, because I'm going to be talking about information theory. I'm drawing an analogy between what I said and the language in information theory, because I'm going to use it later when I throw out words like tensor networks or things like that. But this is the level. But let me say it because I might forget. Later on, when you talk about quantum systems, your x is going to be still x. We're going to see examples of this. Your P of x is going to be replaced by the density matrix. So your task becomes using the correlations in the density matrix to compress and represent the same density matrix in a smaller dimensional Hilbert space. This is exactly the essence of tensor networks in information theory, in quantum information theory. You use the correlations to compress and express them efficiently. This was maybe too quick, but I'll come back to these comments. All right.
Just to say, suppose that there are two letters.
Yes.
Namely 0 and 1.
Correct.
And then the state would be some bunch of 1, 0, 0, 1, that kind of.
No, the state would be a probability distribution like this. A state would be probability a third is the source. Probability a third for 0, probability 2/3 for 1. That's what the state is. It's a source. It's English language, which produces A's with a probability, B with a probability, and so on and so forth.
How about the phases?
Sorry?
How about the phases?
Phases. Oh, this is classical. This is a billion. At the moment, it's a billion. All right. So now we want to move towards, with this simple example, intuition in mind, that every classical system is, every classical algebra, this classical system is the algebra of bounded function on a measurable set. We want to move towards quantum mechanics. So we want to start with this von Neumann algebra and construct something that's non-abelian. Cross product comes to our help. So this is where things are done. One way to do it is using cross product. So let me just work out an example. I'm going to erase this part because I want to draw. So let's pick an example where your x is just x1 to xd, d points. Your state is a probability distribution on this, which I can represent using a diagonal density matrix. I already wrote it like this. Now, imagine you have a symmetry. I don't have to have this, but because it's an example, I can do whatever I want. What is the symmetry I'm talking about? Let's say your state was 1 over d. It was maximally mixed. Such a state has the symmetry. What is the symmetry? It's all the symmetries of x are going to be symmetries of the state. For example, all permutations. What are the symmetries of x? All permutations. X goes to sigma of x. Sigma and SD. All such permutations leave this state invariant. In the Hilbert space language, these permutations are generated using these relabeling unitaries, right? So these are relabeling unitaries that do exactly this. So actually, this is a particular relabeling unitary. Right? Now notice that clearly this relabeling unitary does not commute with your row, because if it did, it would not act on it. It would just cancel. So these symmetries act in what mathematician calls an outer automorphism. Automorphism means you take the algebra, map it to itself, and that map is linear and respects multiplication. It's outer, meaning that it's not inside the algebra. So you have a bunch of symmetries that are not inside your algebras but act nicely on the algebra. What you would like to do is you would like to take your algebra, extend it by this group. What does that mean? It means that this is an operator that was not in your algebra. Mathematicians teach you something called cross product, which is a canonical way of extending your algebra by including this operator in it. So what generates the symmetry, you promote it to your algebra and close it. This is what this fancy language means.
Sorry, why is this not part of your algebra?
Oh, because if you commute, these are all commuting things. If these two guys commute, this is going to come here, cancel out. Right?
So can you say again why u of sigma is not part of the algebra to begin with?
So the algebras are diagonal.
This is I am thinking about x1 to xd are different configurations of a system, and rho
Okay, sorry. Maybe I should write this down. So here's it's an abelian algebra I'm dealing with. This is your set X. Your algebra is all functions on X. So which means f is sum over x, f of x, xx. It's an algebra generated by these guys. This is a state on it.
Yes.
The algebra is obviously all the members of the algebra are diagonal in the xx basis. This guy is not. It's not in the algebra. Right? So now mathematicians teach you this thing called cross product. It's nothing fancy. It looks fancy. Well, it's actually not all that fancy, but I want to avoid the definition of it because it's an extra terminology. It's written this way. This is it depends on the representation. I already gave you a representation of how the group acts. So this is what alpha means. So what it does is that it takes your algebra, extended by including u in it. Now, the moment you include these u's in it, what do you obtain? You start with an abelian algebra. You obtain the algebra of a qubit. You get something non-commutative, which is the algebra of a qubit, which is d by d complex matrices. Now, this framework is very, very general. You start with an abelian algebra, your favorite abelian algebra, which is always an algebra of functions on some set X. This set X will have symmetries that you could use to extend your algebra.
Can I think about it in quantum mechanical systems? Can I think about it like this? That my algebra was, let's say I've given a small subspace, and then there is an algebra associated with that subspace. But there are symmetry operators which are not really local operators.
So sorry, let me say one more thing. This setup is about the algebra of the whole thing for now. Of course, I can use it for the algebra of subregion.
Right, but still these are algebra generated by local operators. Of the whole subspace, but generated by local operators. Too easy.
I think to add locality is an extra level of complication. I'll come back to it. The reason I'm reluctant to talk about that particular case is that there is more structure there. It's not the first example. There will be intertwiners and stuff. So the simplest case is when you have just one algebra, no locality.
In this case, your original algebra was just, as you said, diagonal matrices.
Correct.
Now you add these arbitrary permutation matrices.
Correct.
And then you ask, what is the full set of matrices I can obtain by multiplying arbitrary
Correct.
permutation matrices and any diagonal matrices?
Correct.
You say you get all matrices.
Correct. That's exactly what it is. And that is the algebra of a qubit. Now, if I repeat this for other systems that you know, I'm going to land on things that are familiar. For example, I'm going to say it, not write it. Take a particle on a circle. The algebra, so circle x1, let me write it down, actually, it's helpful. So take the example where x is S1. Then your states are, your algebra is f of thetas, functions, bounded functions of theta. Your state is a probability distribution of theta, right? Now, what is the symmetry you're going to be talking about here? Symmetries of x. What are the symmetries of x that are natural here of S1? Rotation is one instance of it. Rotation by theta, which is alpha, del theta. Well, clearly, this acts on this it has an action on space of functions on S1. It's an outer automorphism because it doesn't commute with this guy. However, all the members of these guys commute with each other. The moment you promote this guy to an operator, you take your abelian algebra, extended by U1, you get the algebra of a quantum particle on a circle. There's nothing fancy about this. Now, here, allow me to come back to your comment about phase space. This is crucially different from phase space because in phase space, what you do is a deformation quantization. You have the phase space algebra of functions. That the algebra, you introduce a parameter h bar. You get a one parameter family of algebras that in the limit becomes commutative. This is not how things are working here.
Yeah, here you're starting with functions just on position.
Exactly. It's
And
an
then you're
abelian
getting
algebra.
momentum out of it.
Correct. I'm getting momentum out of symmetries, outer automorphisms.
Yeah, well, when you do this geometric quantization game, so you start with the phase-based functions,
Yes.
FXP. So normally your given with respect to averages of fxp.
Yes.
Meaning that, you know, some distribution like in classical statistical mechanics, that's what you do. Then you say that, well, of course, this fxp I cannot directly quantize.
Yes.
So this is this step called pre-quantization.
Yes.
So these guys are not phase-space functions because you have now imposed this pre-quantization thing here, or
I'm not quite sure how they're.
Well, he has made a choice of polarization in which his coordinates are only positions.
but I lost, classically, I would use some information. I mean, my, you know, the expectation values are with respect to some fxp. So, I see, if the observables are only functions of x maybe, then I can integrate out.
So you see, the thing that's happening is that in this case, your x always remains a simple, smooth geometry. Whatever, a set of points or something, you do not change x. What you do is that you start with functions on x, you enlarge it by introducing operators. Now, in deformation quantization, what happens, sorry, in geometric quantization, if I understand correctly, I'm no expert on this, you start with a space, that's geometry, you replace it with something non-commutative. Something non-commutative and things are more complicated. But this is different nature. This is of different nature.
Yeah, I mean, I don't think it's classical. It doesn't sound to me like the classical is classical or classical physics. It was just some classical algebra in the sense that it was
Yes.
commutative.
Yeah.
Kind of image.
Not even a no, because I don't think in his example you weren't getting phase space, in coordinate space.
Yeah.
The word classical is used.
So but what is important is that, okay, so in the next example, which is going to be very clear based on what I just told you.
I understand now this would be a quantum mechanical particle of algebra of that if you use this particular symmetry, namely the U1 that rotates
Correct.
S1. But here you were giving examples of some discrete groups and so
Yeah,
on.
yeah, sure.
So here also you could use just that.
If you take an
subgroup of discrete subgroup of
you
that.
get other, you get the Hilbert space of, say, periodic functions and things that funny like that. But I'm using this as I decided by saying, I motivated this by saying this is a tool to generate new algebras, non-commutative algebras. So what is neat is that, well, in the second you'll see the second quantized Fock space is also like has a similar structure. It's not surprising.
If you interpret it as algebra of periodic functions or some other thing, then I mean the coordinate space and phase space are conjugate to each other in some sense. But here your coordinate space is always S1, but your momentum space can change. So
I don't have anything intelligent to say about the connection with geometric quantization, but I can only tell you it's different.
okay, some algebra.
I can only tell you it's different.
And what was the importance in your construction of starting with the use that was symmetries of your state?
So I said symmetry because it's for physicists it's more familiar to saying an outer automorphism. But what it was that I wanted a group that acts on my algebra in a natural way that's not part of it. Every time I have that, I can enlarge. There's a mathematical canonical way of enlarging, and then when I do it, I find familiar examples. So for example, if I take my x to be n copies of S1, then this guy induces an action on the algebra of functions of n variable, right? And then, of course, you can see that you get the quantum mechanics of n particles on a circle. Then you can have bosons and fermions, symmetrizer, anti-symmetrizer, all that. You can direct sum them. You're going to end up with, okay, so this is just, I'm sketching it. So the algebra of 1 particles, 2 particles, and so on and so forth. So here to just motivate it, then you say, what if you have this operator that takes you from sectors to sectors that is not part of your algebra? Here your algebra is abelian, right? Now, this does not introduce a structure of a group. This is not a group. However, it's something similar for which cross product generalizes to. You could add this operator to your algebra, you get the second quantized Hilbert space. So all I'm saying is that this is a useful tool. Cross product is a useful tool.
If I just say once more what I understand. So you basically started with local operators like f of theta.
Yes.
And you added some some non-local operators, some symmetry operators, which are this u alpha. So this is your bigger space now. You have local operators and some symmetry.
What is the local operator here?
I was thinking about f of theta as a local operator. theta is my space direction.
F is a function everywhere on a circle, so what is
Right.
local about it?
So it's localized at theta. So f of theta.
No. F of theta means a function on theta. F of theta means like if this is 0 and this is 2 pi, f of theta is this. It's some function. It's not localized necessarily anywhere.
When you say something is
But
slightly
it's
different,
sorry, let me just complete this. Okay, so when we do quantum mechanics, we level them. Let's say quantum field theory, we say that O had some operator at location x. So here I'm thinking about O is an operator at location theta. So I was
I think you should be thinking of position representation of single particle.
Yeah.
Yeah.
It's f of q. F of the operator x. Yeah. In his example, because his original classical thing was just functions of one derivative. So that's like position space. Operators like f of position, and now he's managing to get f of momentum with this. So I'm just sorry, you should complete that. I was just saying, don't think of quantum field. That's
Yeah.
okay, let's think about quantum mechanics.
Yeah.
In quantum mechanics, you can have operators which are positions.
Yeah.
They will have parameters like position at time t.
There's no time. Just fill that.
At a given time slice, you just have position at some point x, which is an operator.
So x is an operator, roughly speaking, but f of x is also.
F of x is also
X is an unbounded operator. If f is bounded, f of x is going to be a bounded operator, so I can talk about an algebra. That's why I take f of x. However, delta of x, the delta function, are bad things because they're not bounded. They do not form a nice algebra. I insist on algebras, therefore I have to talk about things that are bounded.
I'm asking this because of the following reason. You can have symmetries which might not be the zero form symmetries. Like you can have more fancy symmetries. And then there might be different ways of extending this algebra. So if you started with A and you extended with the symmetry group,
Yeah.
a symmetry group might not be related to a zero form symmetry.
Sure, there are all sorts of things you could extend it with. Here was just like one example I pulled out of a box to motivate the tool.
Right. So
I'm not saying there's anything. I'm not saying there's anything deep about this example. It was just an example where you know where you start, you know where you land. It's all under control.
More
So
generally, it's an outer automorphism. Right?
it's an outer automorphism. That's all I care about. I don't even have to say symmetry because it's irrelevant to this problem.
doesn't have to preserve the p of theta that you start with. It
So
has to, right?
if it preserves that, then there's a natural way of talking about the symmetry. If it doesn't preserve it, it's not even it's just an outer automorphism.
Because you want
I don't
to
need
extend
to.
the
I don't
algebra,
need to
it
that.
doesn't care- You
Yeah.
don't quite care about the state.
I don't care about the state. I just want to generalize it to algebra. All right. Okay, so now we finally get to quantum field theory. So the very first example of quantum field theory, which is going to be fermions and 1 plus 1 dimensions. So I can work with algebra. So now I have some psi of x. I can integrate this psi of x with some f of x. We call it psi of f. If this f is only supported in space, that's fine. I can take f to be supported in space-time, in which case you have to take f to be the solution of the classical equations of motion. But it's a little bit more fancier, covariant way, but fancier way of saying it. But for simplicity, less restricted to time slices. So this is one function. You know what the dagger is.
So this need not be linear in field also, right?
Yeah. So I just wrote down a function,
Some
right?
functional.
Yeah, exactly. So these guys, this is a bounded operator because psi of f dagger psi of f is the integral of d of x f of x squared. If I pick, so now, oh, I'm sorry. That's not what I wanted to say. Sorry, no, that's not what I want to say. Let me define an operator O of f, which is d of x, f of x, real function, psi of x plus psi dagger of x.
Psi of x is the usual fermion operator.
I'm connecting it with so this is an operator value distribution. It's not, yeah, you use it to generate the algebra with it. So a self-adjoint. And furthermore, it squares to f of x squared. If I pick f of x so that this is 1, It's a self-adjoint operator that scores to 1. That's called a projection operator. So a projection operator in the algebra is some operator P that's self-adjoint and scores to, oh, I'm sorry, scores to, that's a bad example. I'm sorry, this is wrong. So this is not a projection operator. Scores to P. It's not a projection operator. This is, I was trying to motivate this incorrectly. Scores to 1. To get the projection operator, you have to pick things that are like step functions, or functions that are supported, that are 0 outside of a region and it's 1 on a region. Okay, so how am I doing on time?
The only constraint is lunch, so maybe 15 minutes we should go.
Okay, so I can cut the intertwiner story and just wrap up by talking about theory of dimensions. One thing that I just using sloppy language I used in this lecture earlier.
I missed the point of this example. What was the punchline?
Oh, I just wanted to give an example of
what?
algebra of quantum field theory associated, algebra of quantum field theory. I talked about bounded operators, right? So if we usually, and we're trying to relate it to things that we do know. Usually we talk about operator value distributions. This is how you would define an operator. Its multiplication rules are well defined using Wick contractions, right? And these operators are bounded, clearly bounded. And yeah, one instance of an algebra they generate.
More generally, this is a functional, right, of the field? Should I think of functional of the field?
Functional of the field.
Just like I was thinking of functions of x.
You could think about it that way. Yeah, I'm not sure if
I mean, this is a linear functional of
Yes.
psi, but there could be more complicated.
But it generates it. It generates functionals, yes.
Wait, psi I'm thinking of as an operator.
Yeah.
That's so it's
So now, to form an algebra,
Previously it was x and operated one again.
yeah, so you have to multiply all sorts of things like this,
Yeah,
right?
so there could be things on this line.
Yeah, so whatever they are, they close an algebra. So that's the algebra we're talking about.
This is a generator, so there is some notion of generator in algebra.
Yeah, it generates it. It generates it. But the point is that this is bounded, so by multiplying them, you always get bounded things and keep going.
So what's a typical state here?
Oh,
There's other information you need to create a representation.
no, a state, sorry.
So if you're an algebra and a state, you have a representation.
Correct.
So you have described the algebra first.
Yes.
So what's the example?
So the state that is typically taken to be the vacuum of Poincare invariant quantum field theory is going to be some Gaussian thing that I haven't written it down, but there's like a in-length discussion of this. All right, so let me just wrap up by talking a little bit about the theory of dimensions. So I talked about, using sloppy language, I said infinite dimensional algebra, but what do I mean by that? What is a dimension of an algebra? So this comes to the theory of dimensions, what the mathematician called theory of dimensions, built by von Neumann. It's fancy for something simple. So the intuition that von Neumann had was that if a general quantum system is a von Neumann algebra, how would you go about studying it? One way to go about studying it would be to study the projection operators inside the algebra. Projection operators are special operators. They are operators that are self-adjoint and square to themselves. So, for example, in the case of a qubit systems, these are projections. Now, one thing that you would like to do is that you could associate a notion of a dimension to projection operators. How would you do that? First of all, let's say you have two projections, E and F. If E projecting the Hilbert space by the action of E is the subspace of the Hilbert space that you get by acting with E is larger than the subspace you get by acting with F, you say E is larger than F. Okay? Now, I'm going to use this in a second. You say if for some unitary U dagger E dagger is F, you say the dimension of E is equal to the dimension of F. All right? Also, if U, so and then you write it this way. Now, if E is larger, strictly larger than E prime, we say dimension of E is larger than the dimension of F. Okay? Now you immediately see this is an ordered set. It forms a partial order. So two things that you would like to understand about the partial order is the smallest element and the largest element, if there exist such elements. If there exists some E such that some projection for all other projections have dimension larger equal to E, then that is the smallest projection. And it makes sense to call dimension of E to be equal to 1, because E acting on the Hilbert space is one-dimensional. It's a one-dimensional subspace. If there exists such a thing, well, an instance of this is 0, 0. If there exists such a thing, we say the algebra is type 1.
Why do I need such a heavy-duty machinery? I mean, what I mean to say is that an algebra is at least a vector space or not?
Algebra is, of course, a vector space, yes.
So that a vector space has dimension.
Yes.
So therefore, the dimension of the vector space is the dimension of the algebra or not?
You could say it that way, but here I'm going to define what is the type 1 algebra, what is the type 2 algebra, what type 3 algebra. Not all infinite dimensional algebras are going to be created equal.
Sure. I mean, this is extra structure, but I'm saying that
Yeah.
just to say that something is an infinite dimensional algebra, I could say that the infinite is infinite.
You could talk about it at the level of the vector space, indeed. Yes.
But we are just given a generating set for the algebra. It's not clear what the dimension is. We want to calculate that.
I think you would associate the dimension to a vector space by constructing a basis.
Yes.
This is what the basis is.
That's what you do.
Yeah, this is exactly that basis. So type 1 algebras have this minimal projection. You can convince yourself that the example of quantum field theory that I gave does not have such thing. Oh, sorry. Does not have such things. To make this a projection, I have to take f of x to be something like this, right? Something like a step function. And then, of course, I can pick a smaller step function, which is inside that. I can pick a smaller step function, and so on and so forth.
So even then I don't understand why would be close to a projection, because if you act it twice, you have two fermionic operators.
Oh, sorry. I meant, no, if you act, oh, this is a bad example. Yeah, I think you're right. This is a bad example. Yeah, you need something that squares to itself. Yeah, this is a bad example. Sorry. Yeah. Sorry. But I one. All right, let me come back to this with examples of projections. They're built out of, I think, for fermions it's a little bit tricky. They're built out of these step functions, basically. So what is important is that, well, okay, if an algebra doesn't have a smallest, is not type 1, so, okay, it's not type 1, but has some projection for which the dimension of it is less than infinite, is called type 2. By the way, infinite dimension, you say an algebra is properly infinite. So, sorry, a projection is properly infinite dimensional if for some f that's smaller to it, they have the same dimension. some smaller projection is unitarily equivalent to it. Then they say it has infinite dimension. Now, if the algebra doesn't have a smallest element, but there exists a finite element, there exists some projection that's not infinite dimensional, then you say it's type 2. And
what is the meaning of that less than sign? So what is the small f smaller than e mean?
here.
Ah, okay. Strictly.
Now, finally, an algebra is type 3 if and only if all projections are equal. What does it mean? It means that any two projections you write down, they're unitarily equivalent. So this is the sense in which I said quantum field theory has lots and lots of unitary operators. There are unitary operators that do all sorts of crazy things. They rescale things. They do all sorts of things. We're going to come next lecture. I'll give explicit examples of these things that rescale and do all sorts of things. There is no finite dimensional projection operator. So one thing just to play around that's important. I think I found it. This is my last comment.
What did you say? There exists one projection operator.
There's, yeah, there exists no smallest one, and there exists at least one finite one.
At least one finite that
Yeah.
is type 2, which is not type 1, but exists one finite that is
Yeah.
type 2.
Yeah.
And type 3 is there is no finite.
Yeah. I can give explicit examples depending on how much time we have.
Sorry, how you are saying there is no smallest one,
Yeah.
but there is a one which has a finite limit.
Yeah.
So, but then,
By smallest, he means one, dimension one.
oh,
Well, it's a partial order set. It's a partially ordered set.
Then I guess if there is one with finite dimension, that is the smallest dimension.
Sorry? No.
There is one for the
No. The projection operators could be dimension arbitrarily close to
Yeah, there is
0.
no number. Like,
Yeah, there's no, it's just,
just the measure.
yeah.
Ordering
They could get smaller and smaller and smaller. This is an example I can construct. I can do it in the next lecture. But let me just finish by, what did I want to say? So all of these algebras are sub-algebra of bounded operators in the Hilbert space. So go back always to harmonic oscillator. So let's write down projections that have finite dimensions. So this is some smallest projection. But I can write down infinite dimensional projections. This is an infinite dimensional projection, right? Now I can write down projections that are, but what is interesting is that if you have a projection in the algebra,
Why is this infinite dimensional projection that one?
this guy,
Projects onto everything.
because this is, yeah, it's just,
Uh-huh.
it's unitarily equivalent to 1.
Unitarily equivalent.
Links to all the excited states.
Everything
Yeah.
except the vacuum is projected
Yeah.
onto it.
So every time you have an algebra, if there's a projection in it, 1 minus that projection is another projection. So if there's a projection, this is a projection. If all of your projections are infinite dimensional, you're looking at things that are, for example, like this, k even. This is an infinite dimensional projection. And 1 minus it is also infinite dimensional. So if you could construct an algebra out of these guys, it would be something like type 3. I'll give examples of this.
The first one is not an allowed projection in QFT if O is a ground state.
Sorry?
The first example,
Yes.
taking O as the ground state of the quantum field theory
Yes.
is not a valid projection operator.
No, it's not.
And
It's not supported in the region. So remember,
you have some notion of boundedness.
so this is, yeah, put the quantum field theory, there's a gap. Put the quantum field theory in a circle, for example, right? So here, the algebra is type 1, therefore this is a projection. However, if you talk about the local algebra, there exists no local operator that projects down to the vacuum. It's just simple.
Local operator is projection.
Well, yeah, the algebra is a local algebra.
Local.
Yeah. I mean, it's the algebra of local operators in quantum field theory that is type 3. That's what's important.
Local operator.
Yes. Of course, if we do any quantum field theory in a circle, it becomes type 1, for sure. Of course. But I guess part of the philosophy is that we want to do physics locally. We want to do quantum field theory without caring about what goes on really, really far away. We just want to do it locally. Here's where I'm doing my measurements. I should be able to describe everything by doing my measurements here.
Right, but once you start extending your local algebra of local operators with this symmetry group G, for me G is symmetry group, then I think you are including operators which are not local. I mean, you are including operators which are also non-local.
So
Because
so the example I gave was the full algebra, right? So, and I say it's an outer automorphism. If I take in local algebra, I can only talk about an outer automorphism of the local algebra. Of course, translation, rotations are not going to be such things.
Right.
So I can talk about things that generate flows like this.
Right.
But I was not talking about that.
If it is finite
Yeah.
set, then you will not
Yeah.
have those. Right.
All right, maybe it's a good place to stop.
This type 1 algebra,
Yes.
is that a subalgebra of the type 3 algebra that lives on the whole sphere? That must be right.
Sorry, say it again.
The type 3 algebra that acts on the whole sphere.
The whole sphere is type 1.
Yeah, so this type 3 is a subalgebra of that.
Yes, this type 3-1 is always inside infinity, sub 1 infinity. All the algebras we were talking about are inside 1 infinity. So in the next lecture, I'll start by constructing examples of type 2 and type 3.
This is about slicing the type 1 algebra in various ways.
Exactly.
And trying to keep the local structure.
Exactly. This is about taking subalgebras, infinite dimensional subalgebras of this harmonic oscillator, such that all sorts of funky things happen with the projections. And quantum field theory local algebra of it is a particular type. Yeah. All right. Thank you.